So what we want to talk about this section is probability. So you've used this in your everyday life without even knowing it. It's something that appears all around you. So we want to kind of talk about how do we go about calculating probabilities of events. So we're going to start because we're going to be working with fractions, and we want to talk about how we can reduce a fraction. So we say a fraction is in reduced form, or also in lowest terms, if there are no factors other than one common to the numerator and denominator. So essentially meaning there's nothing I can divide the top and bottom by. It is in the simplest form. So we'll try just two examples. We're going to reduce if possible. So if I look at 4 divided by 6, I could plug that into a calculator, but you see it would not be a pretty number. And I want to leave these things as fractions. So if I want to reduce this, 4 and 6 are both even numbers. So I can go ahead, divide the top and bottom by 2. So 4 divided by 6 is the same thing as 2 divided by 3. Okay? And then looking at 2 and 3, I can't divide either of these by anything except 1 and get a nice number in return. Okay? So let's do the same thing with 30 divided by 12. You might not be able to get the biggest number that goes into both of these at first, and that's okay. So maybe you recognize, okay, well, 30 is divisible by 3, and so is 12. So let me start by doing that. Let's take the top, divide it by 3, and the bottom, and divide it by 3. So if we do that, that leaves us with 10 in the numerator, and then 12 divided by 3 is 4. And then, well, I've still got even numbers here, so 10 and 4 are both divisible by 2, so I can keep going. I can keep dividing something out. So we take top and bottom and divide it by 2, and that leaves us with 5 over 2. And now 5 and 2 share nothing in common because 5 is only divisible by 5 and 1, and 2 is only divisible by 2 and 1. So that is in lowest terms. Okay, but see how I had to take 2 steps here? That tells me there was actually a bigger number that divided into 30 and 12 from the start. So really both of these are actually divisible by 6. So if we do top and bottom divided by 6, it leads us to 5 over 2 in a quicker manner. But it's perfectly okay if you take a long route, not a problem, especially when you have big numbers. If you find it's divisible, just keep going. You'll eventually get to the end result. Okay. So now we're going to be working with fractions a ton because we want to talk about how likely it is for some event to occur. And that's exactly what the probability of something tells us. So the probability of an event occurring is a description of how likely it is that event will happen. So you're going to express this in one of 2 ways. So if you think about the chance of an event, you could think of it as a percentage. So it could be given as a percentage between 0 and 100. You can't have a negative chance something is going to occur. You also can't have more than 100% chance that it will occur. Okay? The other way you can display the same information, because remember, percentages you can always put in a decimal form. So we can also give this as a decimal or fraction between 0 and 1. So we have this scale, 0 being the smallest and 1 being the biggest. So at one end, we have a 0% chance, which corresponds to 0, or we have a 100% chance of the event happening, which corresponds to a 1. Okay. So if you think of a 0% chance that it's going to occur, this would mean the event is impossible, if you want to think of it in nicer terms. If you have a 100% chance it's going to happen, you can say this event is certain or guaranteed. Okay. So you see this often with the weather. It tells you there is a 70% chance it's going to rain. That means it's really likely that it's going to rain tomorrow. Doesn't necessarily mean it's going to happen, but it's likely the event will occur. So right smack dab in the middle would be then a 50% chance, which corresponds to 0.5. This means there's an even chance of that event occurring. The best example you can think of is tossing a coin. 50% chance it lands on heads, 50% chance it lands on tails. You have a 50-50 chance of one of those events occurring. And then anything in between these you can classify as one of two things. So if it falls in that 0 to 50% chance, it's unlikely. But again, it doesn't mean it won't happen. It's just unlikely. And then 50 to 100, there is a likely chance this will occur. So we're going to kind of talk about just nicer situations, because a lot of realistic things you can't necessarily put a true percentage on. We're going to work with cards. We're going to work with decks or decks of cards. Then we're going to work with rolling die. We're going to combine the two. We'll see a lot of different things and work with things that we can calculate what we call this theoretical probability. Because what happens is I can basically determine what's the possible chance of this occurring. But in practice, if I roll a die 500 times, it doesn't necessarily mean what I think is going to happen will. It just means the more and more that I would roll these, the liker it is to get to what I think is this theoretical probability. So you're going to see this popping up in your homework, these two words, theoretical and experimental. Theoretical is just here, given all of these outcomes, this is the raw, true chance of what can happen. Experimental is if I actually try this out, if I roll a die 1,000,000 times, how many times did I land on a 1, 2, 3, 4, 5, 6? So it's out of the experiment. The more times you do the experiment, the closer it is going to get to that theoretical probability. Okay. So let's look at an example. We're going to roll a 6-sided die. If we think of the possible outcomes, just your standard dice that's in any of your board games like Monopoly, you can roll a 1, 2, 3, 4, 5, or 6. Okay? This is called the sample space. It is all of our possible outcomes for this event. When I roll the 6-sided die, these are the 6 options that I can have occur. So if I want to figure out what my chance of rolling a 4 is, out of all of these, there is one event that makes me successful. So our probability is there is a 1 in 6 chance of rolling a 4. So if you plug that into your calculator, you would see this is about 0.17 as a decimal, which means that there's about a 17% chance of rolling a 4. Okay. So this is that theoretical probability. It is just the chance that I have, because there is one chance out of 6 outcomes that this event occurs. Okay? And that's all we're doing when we're calculating a probability. We're trying to see how many ways does this outcome occur out of all of my possible outcomes. So the way we typically would write this, just to kind of show you with this example, is I would say the probability, which is that P, of rolling a 4 is 1 out of 6. Okay? And the directions will tell you, do you leave it as a fraction? If it doesn't say anything, that means it is a nice number. You leave it as the fraction 1 over 6, or it would tell you to round to however many decimal places if it wants that. Okay? But to find the probability of some particular outcome, you're going to take the number of ways that outcome can occur, and you're going to divide it by the total number of outcomes for that situation. So one of the best things or best examples we have with probability is working with a deck of cards. So if you're not super familiar with what's in your deck of cards, here's the list of all 52 cards in a standard deck. So to kind of go over, you have two different suits or two different colors. The cards can either be red or they can be black. Then you have 4 possible suits: hearts, diamonds, spades, and clubs. And then within each of these suits, you get one of the cards: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So those are all the different possible cards. And then jacks, queens, and kings are considered face cards because when you draw them, they have a face on them. Whereas if you were to draw an 8, you would just see an 8 on it, or you might see like 8 hearts. It just depends on the deck of cards, okay? So what we're going to do is from this standard deck, we're going to draw one card at random. So out of these 52 total cards, I'm going to pick a single one from somewhere in the deck. What I want to do is I want to figure out a couple different probabilities based on these particular outcomes. So the first one is I want to figure out what is the probability that the card drawn is red. So what I want to do to find the probability of a red card is I want to take the total number of cards in the denominator. These are all my outcomes. And in the top, I want to find the number of red cards. Okay. And that will be how I calculate my probability. So I could go and I could count each and every one of these. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26 cards that are red. So our chance of getting a red card is really 26 out of 52 total cards, okay? But unfortunately, this is not fully simplified. So I can divide each of these. They're both even numbers, so you could start by dividing it by 2. But really, both of these are actually divisible by 26. So if I take top and bottom and divide it by 26, that leaves me with 1/2. So there's actually a simpler way to do this because there are 26 red cards, but there are also 26 black cards. Okay. So another way that you could think about this is really based on the number of colors in the deck. There's 2 colors, and we're looking for 1 red color out of the 2. Okay. So instead, you can approach it this way. In the same way, if I'm trying to figure out what is my chance of drawing a heart, well, in that case, 1 of 4 suits are hearts. So I have a 1 in 4 chance of drawing a heart. But again, I could go ahead and I could calculate there are 13 hearts out of 52. So my probability would be 13 out of 52, which would simplify to 1/4. So tons of ways that you can go about this. If I wanted my probability of getting a face card, well, here I've got 12 face cards out of 52 cards. So my probability is 12 out of 52. But the other way I could look at it, if I figure out all of these cards, 3 out of 13 types of cards are face cards. So your probability is 3 out of 13. So tons of ways that you can go about this to really immediately put it in that simplest form. Okay. Let's try a couple more of these, working still with this deck of cards. We want to figure out what is the probability that the card drawn is a 7. So looking at 7s, there are 4 of them in my deck. So the probability of getting a 7 is 4 out of 52. Okay. But again, if I want this fully simplified, it happens to be that both top and bottom are divisible by 4. So it leaves us with 1/13. And again, the other way I can look at it is I'm looking for one specific card out of 13 types of cards. So I have a 1 in 13 chance of getting this particular card. So hopefully so far this isn't so bad to think about it. The problem is when we start then combining events. So I'm still going to draw one card at random from this deck, and I want to figure out what is the probability the card drawn is red or a 7. So as long as my card is red or a 7, I'm good. I'm making this event possible. The hardest thing though is figuring out the number of cards that fit that event. A lot of times what would happen is people will go, okay, well, there were 26 red cards. There were 4 7s. So in total, there's 30 out of 52 that make this event possible. But that's not the case here because you're counting overlap. So instead, if I'm looking for a red or a 7, I know I've got all 26 of these red cards that make this event successful. And then because I can get a red or a 7, I've got 2 extra ones that make this event possible. So I'm not double counting the ones that fit both of the categories. So really here, there are 28 cards that are reds or 7s. Okay? As long as one of those criteria works, I'm good. So you have to be really careful with the language. So there are 28 out of 52 cards that make this event successful. So our probability of drawing a red or a 7 is 28 out of 52. And then to simplify this, both of these are divisible by 4. So my reduced form for my probability is 7 out of 13. So again, be very careful. The word or means as long as I have one or the other, I'm good. If, however, I change this slightly and I said, what is my probability of drawing a red and a 7, completely changes the meaning of this problem. Because and means it has to have both of those criterias. So I need this card to be red and a 7. And in that case, only 2 out of 52 cards fit this category. Okay? So pay very, very, very close attention to the words that are used. So remember, and or have very different meanings from our Venn diagrams. So the very last thing we're going to talk about with probability, and again, this is going to be a more difficult section because it is harder for a lot of people to grasp. Take your time with it. Make sure you have ample time to go through, try lots of problems, get some extra practice with it. So with these probabilities, we can also calculate something called odds. And typically where you've seen these or heard these before are typically in some kind of betting, and more commonly in sports. So you often see this if you ever watch the Kentucky Derby. You have odds on a horse winning the race, and it might be something really random like 506 to 1. And then those odds give you some kind of betting mechanism. So your odds could be good, your odds could be bad, and that determines how much money you would make if you bet on these particular things. So what the odds do is it's really comparing 2 different probabilities. When I have a race occurring, the horse is going to win or it's going to lose. There's no in between. One event will occur. So it fails or it succeeds. So we have 2 types of odds, the odds against an event occurring, and then we also have the odds in favor. And all you're doing is comparing these 2 probabilities. So when I look at the odds against an event occurring, we're going to take the probability the event fails to occur and divide it by the probability the event succeeds or occurs. Okay. So if I'm looking at the odds against a horse winning, in the top it would be the probability it loses divided by the probability it wins. So you can think of this as the probability of failure divided by the probability of success. Okay. When you calculate odds in favor, you really don't have any extra work that you have to do. It just determines which one comes first. So here, this is going to be the probability the event occurs in the numerator divided by the probability the event fails to occur. So it's really success first, followed by failure. And so we're going to calculate an example with this, but typically when you think of odds against a race, you're not seeing it as a fraction, but instead you're seeing something like 5 to 1. Okay? So all that means is we're going to kind of figure out how the denominators of our probability disappear. But that's because when I'm looking at the probability of an event failing to occur and the probability of it occurring, the denominator is going to be the same for both. So it'll actually end up canceling each other out. So really we're just going to take the numerators, or the number of outcomes or number of ways the event fails and the number of ways the event occurs. We're not going to care so much about what we divide it by. So we'll do an example and see all the different ways that you can write these odds in favor and odds against. So the way we're going to look at it is we're going to work with a charity raffle. So Philippe won a charity raffle. His prize is going to be selected from one of these 9 prizes. There are 3 rings, 1 camera, and 5 headsets. So we're going to figure out the odds against Philippe winning a ring and the odds in favor of him winning a ring. Okay. So when we go about this, we need to consider what is our success and what is our failure. So if I want the odds against winning a ring, we need failure in the top and we need success in the bottom. And since our ring is the key event, failure would mean we don't get a ring. And success means we get a ring. So I want to calculate these 2 different probabilities, okay? So starting with our probability of not getting a ring. Okay. Looking at our depiction of all of these, we have 1, 2, 3, 4, 5, 6, or really going back up here, 1 camera, 5 headsets. There are 6 out of 9 possibilities that result in us not getting a ring. So our chance is 6 out of 9. Okay. And again, I want to put things in the most reduced form. So I'm going to go ahead and divide both of these by 3. And the reduced form would be a 2/3 chance of not getting a ring. Now to calculate our probability of success, that's the probability we get a ring. And there are 3 rings out of 9 prizes. So our probability is 3 out of 9. Which, if we go ahead and reduce, both of these are divisible by 3. So there is a 1/3 chance we get a ring. Okay. So a couple things I want to point out before I actually calculate my odds. If you look at these 2 numerators, 6 and 3, they exactly add to the denominator 9. Even in the reduced form, 2 plus 1 gives us that denominator of 3. So really the numerators tell us everything I need to know about my total number of outcomes or my chances within here. So now when I go to find my odds against the ring or winning a ring, we put failure in the top, which is 2/3, and success in the bottom, which is 1/3. Okay? But we definitely don't like fractions and fractions. So what I'm going to do is we can always take the top and bottom and multiply it by the same number. In the same way we can divide by the same number. So if I multiply the top by 3 and the bottom by 3, I'm not changing anything. And what that does is it actually makes those 3's disappear and leaves us with 2/1. So again, all that really left us with, just go and try to get rid of these highlights to show you. The denominator did not matter at all. All we were left with is 2/1. So our odds against winning a ring are 2-1. So you can write it as this fraction. You can write it in the typical way you're used to seeing odds, 2:1. Or you can also write it as 2-1. Those are your odds against winning a ring. Okay. So essentially, you're just caring about the numerator and the probabilities because they end up disappearing or the denominator ends up disappearing when I put it in this fraction. So to show you with this next example, if you find the odds in favor, all that means is we switch the order of these. So we put success in the top and we put failure in the bottom. Okay. And I'm going to even show you with the unreduced fractions how we get this. So our probability of success, or probability we get a ring, is 3 out of 9. And our probability we don't get a ring is 6 out of 9. So in the same exact manner, because these are both being divided by 9, we times the top by 9, and it leaves us with the numerator 3/6. Okay. So 3/6. So your odds would be 3-6, but that's not reduced. So if I want to put it in that reduced form, 3 and 6 are just both divisible by 3. So really at every step, you would take each side and divide it by 3. And so your odds in the simplified form would be 1/2, 1-2, or 1-2. And all that did is just switch the order of which came first. So once you have one, you don't need to go through the effort of doing the other. Just switch the order. That's all that happens. And again, the denominator really doesn't matter in these instances. It's just the number of ways that event happens in the top, number of ways the event doesn't happen in the bottom, or vice versa, depending on the odds you're taking. Okay. So one thing you're also going to have to be able to do is if you're given the odds, you need to reverse engineer the probabilities. And so I want to see if you're going to be able to do that, but to kind of just give you an insight, if I were to reverse engineer the probabilities from these odds, this would tell me my denominator in both of my probabilities is going to be the sum of them, 1 + 2 or 3. So since this one is the odds in favor, my probability of success will be the first number divided by 3, and my probability of failure will be the second number divided by 3. Okay? So the two numbers in your odds add up to the denominator. So see if you can try to reverse engineer with different problems what the probabilities are.